Okay, so welcome to section 4.3 and 4.4, logarithmic functions and their graphs. So logarithmic functions and their graphs. I don't like the way that looks. Graphs. There we go. Okay, so definition. So a logarithmic function, that's what we're defining. A logarithmic function. Okay. Function. Underline, that's what we're defining. Is of the form. F of x is equal to log and then a subscript a and then an x. So read aloud. Log. So log base a of x such that a is greater than 0 and a is not equal to 1 and is equivalent to oh, I guess I should make that 2 words, equivalent to a to the f of x is equal to x. So let's note, what do I mean by that? Remember, f of x is a fancy way of saying y. So y is equal to log base a of x is equivalent, meaning the arrow goes both ways, is equivalent to saying a raised to the y is equal to x. So we have a little circle, a raised to the y is equal to x. Okay. So recall the second step. And crux. That's supposed to be an x. Crux of finding the inverse of a function f of x. A function f of x is to swap x and y. Okay, we'll consider a to the y is equal to x. Well, this would imply that a to the x equals to y is the inverse. That is, i.e., id est, i.e., the inverse function of f of x being equal to, okay, what in the heck is going on? F of x being equal to log base a of x. Okay, I guess the universe does not want me to write this over here. Okay, listen to the universe, come back over here. So the inverse function of f of x being equal to log base a of x is f inverse of x is equal to a to the x, because these two guys here are equivalent. Okay. So given that, let's go ahead and try and plot logarithmic functions. So example, plot the following logarithmic functions. Following logarithmic functions. Okay, so number one. Let's say we have that y is equal to log base 2 of x. Okay, so we want to note what's an equivalent way of saying this? If we have y is equal to log base 2 of x, this is equivalent to saying, wow, that's a terrible arrow, 2 to the y is equal to x. So we can say this is equivalent to saying 2 to the y is equal to x. Okay, so let's do an x and y chart. Pardon me. X, my goodness, all of a sudden it's so smoky I can barely breathe. So x and y. Well, let's do, well, how about this? What is x? Do you agree that x is 2 to the y? Let me put that equals 2 to the y. Okay, so let's have y be -1, 0, 1, and 2. That means that x will be 2 to the negative first, which we know to be 1/2, or 2 to the 0, which any non-zero integer or number, real number, to the 0th power is 1. Or we have 2 to the first power. Anything raised to the first power is just itself. And last we have 2 squared. Really? 2 squared is equal to 4. So we have the 4 points as follows. So let's go ahead and plot these x and y coordinate axes. X and y, so let's do 1, 2, 3, 4. 1, 2, 1. Okay, so the first point is going to be at 1/2, comma, -1. The second point will be at 1, comma, 0. The third point is at 2, comma, 1. And the fourth point we have is at 4, comma, 2. So what this looks like is something like so. Okay, I guess it's not going to do a nice curve for me. Let's see if I can. Ah, there we go. Okay. Will it give me a logarithmic curve? I don't know if it will. I think these are parabolic curves that they have preloaded. So, but hopefully we get kind of the idea. Okay, good enough for government work. Okay, so this is an estimate to the graph of log base 2 of x. Okay, so let's do another one. Number 2. Let's say we have y is equal to log base 3 of x. Okay, so we have y is equal to log base 3 of x. Well, we know that that's equivalent to saying 3 to the y is equal to x. Did I get the... Okay, so let's do an x is equal to 3 to the y versus y chart. Let's have y be -1, 0, and 1. So we have 3 to the negative first is going to be 1/3. we have 3 to the 0. So anything to the 0th power is 1. Then we have 3 to the 1st, which is just itself. So it's just 3. So we have these points. So let's go ahead and plot these x and y coordinate axes. Make this one smaller. X and y. So 1, 2, 3. 1, 2. 1, 2, 3, 4, 5, 6. Okay, so my first point is at 1/3, -1. Then at, actually let me do that in purple. So 1/3, -1, 1 comma 0, and 3 comma 1. So I'm going to have a nice logarithmic curve that looks something like so. Okay, note that each of these seems to terminate or be a bit larger than 0. Let's see if this. Okay, maybe I have to zoom in to make it better. I know what I'll do is I'll make it over here and then move it. There we go. So there's my vertical asymptote. So both of them, let's see, copy, paste. Both of these have a vertical asymptote along the y-axis, right? And it's because these are inverses of the exponential functions, which have horizontal asymptotes on the y-axis. Sorry, on the x-axis, 1, 2, 3. Let's do y is equal to log base 4 of x. So we have y is equal to log base 4 of x, which we know to be equivalent to 4 raised to the y is equal to x. So doing an x versus y chart, where x is equal to 4 to the y. Y, let's have y be -1, 0, and 1. So then we will have 4 to the -1st power, which is just 1 over 4 to the 1st, or 1/4. Then we have 4 to the 0th power. Anything to the 0th power that is not itself 0 is 1. Then we have, what are you doing? Then we have 4 to the 1st power. So 4 to the 1st power is just itself. So we have these 3 points at the very least. Okay, so x and y coordinate axes. One, 2, 3, 4. 1, 2, 1. Okay, so the first point is at 1/4, comma -1. Then 1, comma 0, and 4, comma 1. So we have this logarithmic graph like so. Okay, so this is log base 4 of x, and the above graph was log base 3 of x. Okay, and we still have our vertical asymptote along the y-axis. Okay, so why is that? Let's recall. Let's see. So recall. That the domain of a to the x, I can plug in any value I wish. So the domain was all real numbers. But the range of a to the x, well, there was no value of x. I could plug in the exponent to get even 0, let alone negative numbers. So it's everything not including 0 and above. So this implies that when we swap domain and range, this means that the domain of log base A of x will be what used to be the range for the inverse. And similarly, the range for a to the x, log base A of x will be the inverse for what it is. So it's just going to be all real numbers. And is that true? My y values go up and down, all real numbers, but my x values are strictly larger than 0. So yes, it is true that the domain and range have swapped. So let's note something. Note that for all y equals to log base A of x, this implies which 3 points are on the graph? Well, we have the point, instead of negative 1, 1 over a, it's now 1 over a comma negative 1 because I swap x and y. Instead of 0 comma 1, we now have 1 comma 0 because I swap x and y. And instead of 1 comma a, we now have a comma 1 because we swapped x and y. These are all on the graph of y. Okay, and also note a vertical asymptote at x equals to 0, which is otherwise known as, i.e., the y-axis. Okay, so given that, let's use transformations. So example. So use transformations. Formations to plot. So number 1, let's say we have that f of x is equal to, let's do log base 2 of the quantity x plus 3 minus 1. Okay, so we have f of x is equal to log base 2 of x plus 3 and then minus 1. So I claim that this is 3 left and 1 down. What is 3 left and 1 down? Well, if I plot the 3 points, which instead of negative 1, 1 over a are now 1 over 2, comma negative 1. And instead of 0, 1, it's now 1, comma 0. And instead of 1, comma a or 2, it's now 2, comma 1. So I claim these 3 points are on the original one, so these will be to be shifted. So prior to shift. Okay, so x and y coordinate axes. So x and y. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3. Okay, so prior to the shift, we had 1 comma 1 half negative 1, 1 comma 0, and 2 comma 1. So what we had then was a graph that looks something like, oh, terrible. I know it goes through 4 comma 2. Something like this, okay? But then I know I'm going to shift each of those points 3 left. So let me change this back to solid. So 3 left. So 1, 2, 3. 3 left. 1, 2, 3. So it's going to be something like so. And then 1 down. So all of those points are now going to shift this solid. 1 point down. So that's the final graph there in pink. Okay, so this is f of x here in pink. Okay, but we also had a vertical asymptote that got shifted from the x-axis to the left 3 units. Okay. Because now the horizontal translation, so this is the line, x equals -3 now, is a vertical asymptote. Whereas before, all of these vertical asymptotes were at x equals to 0 as a vertical asymptote. X equals to 0 as a vertical asymptote. X equals to 0 is a vertical asymptote. Okay. Let's do another one. Let's see. What should I do? I think I can fit it on here. So 1, 2. Let's say we have that y is equal to log base 3 of x plus 4 plus 2. Okay, so we have f of x is equal to log base 3 of the quantity x plus 4 plus 2. So I know that we're moving 4 left and 2 up. What are we moving 4 left and 2 up? The 3 points, which are, instead of -1, 1 over a, it's 1 over a, which is 1/3 gamma -1. Instead of 0, comma 1, it's now 1, comma 0. And instead of 1, comma a, it's now a, comma 1. So 3, comma 1. Okay, so x and y coordinate axes. One, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. Okay, so normally we would have the 3 points at 1/3 -1, 1, comma 0, and 3, comma 1. But each of these is going to be shifted left 4. One, 2, 3, 4. Okay, and then up 2. One, 2, 1, 2, 1, 2. Okay, so that's my f of x finally. And notice that there's going to be a vertical asymptote now shifted to the left 4 units, right? Okay, why is this not clicking? It should click. Okay, so the vertical asymptote will be at x equal to -4. It's a vertical asymptote. So I think we got that. Okay, let's do another one. Number 3. Let's say we have that y is equal to log base 1/2 of the quantity x minus 1. So we have y is log base 1/2 of the quantity x minus 1. So that's simply to the right 1. Right 1. But what is moving right 1? Well, the 3 main points. So the 3 main points are, instead of -1, 1 over a, It's 1 over a, which is 2 in our case, and negative 1. And instead of 0, 1, it's 1 comma 0. And instead of 1 comma a, it's now a comma 1. So these are the 3 points that are going to be shifted to the right 1 unit, so x and y coordinate axes. But what does this look like? Let's see what this looks like. This is a bit of a tricky one. 1, 2, 3, 4. 2, 3. Pardon me. 1, 2, 3. 1, 2, 3. Okay. So normally it would be 2 comma negative 1. 1 comma 0 and 1/2 comma 1. So it looks like if I have a fraction, my logarithmic function seems to be a reflection about the x-axis instead of the y. And this is what I'm going to shift to the right 1 unit to get the final function. So to the right 1, to the right 1, to the right 1. I get a function that looks something like so. Oh, oops, nope, not drawn very well. Let's see. Like so. Okay, so this is my y. And notice that my vertical asymptote is shifted to the right 1. Paste. Okay, so because everything's shifted to the right, we know the vertical asymptote is at x equals to 1. Okay. One more for good measure. So number 4. Let's say we have that f of x is equal to 3 times log base 2 of x, from which I'm subtracting 2. So there's no parentheses, so the way this is written, so we have 3. Maybe I'll do that in green. So 3 times log base 2 of x, and then minus 2. So I have no horizontal translation, but I do have 3 times as tall. And I do have down 2. Okay, so what is 3 times as tall and down 2? Well, negative 1, 1 over a is now 1 over a, so 1/2 comma negative 1. 0 comma 1 is now 1 comma 0. And 1 comma a is now a comma 1, so 2 comma 1. Okay, so these are the 3 points I'm going to make 3 times as tall. So, and then down 2. So x and y coordinate axes. X and y. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4, 5. Okay, so the 3 points I have are at 1/2 comma negative 1, 1 comma 0, and 2 comma 1. So we have our logarithmic function, something like so. But now I'm going to make it 3 times as tall. So in order to make this 3 times as tall, 0 times 3 is still 0. Negative 1 times 3 is negative 3. Positive 1 times 3 is positive 3. So what we get now is this very elongated and thin logarithmic graph, something like so. 3 times as tall. And that's what we're going to shift down 2 units, that 3 times as tall guy. So now that is 1, 2, 1, 2, 1, 2. So what we get, something that looks like so, down 2 units. So this is f of x right here. And notice I didn't shift horizontally. So my vertical asymptote is still the y-axis because I did not shift right or left. So the vertical asymptote did not shift. I hope this is making sense. Okay, so let's recall. Maybe I should have done a note. Yeah, let's do a note. Note. Sometimes logarithms are easier to plot by plotting their T-H-E-I-R. My goodness. T-H-E-I-R. Inverse functions. Then reflecting about the line y equals x. About the line y equals x. Okay, so for example, let's just do example. Plot f of x is equal to log base 2 of x by first plotting its inverse. Okay, so if we have y is equal to log base 2 of x, I know that this is equivalent, or this means that, well, this is equivalent to 2 to the y equals x, and that implies that the inverse is going to be f inverse of x is going to be 2 to the x, because I swapped x and y. So I'm going to plot 2 to the x. So x are my coordinate axes. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2. Okay, so if I plot 2 to the x, I know negative 1, 1/2, 0, comma 1, 1, comma 2, 2, comma 4. So the plot of 2 to the x is this nice exponential curve like so. Well, not very nice, but there we go. 2 to the x. And that the horizontal asymptote for that was just above the x-axis, or is the x-axis, but I'm going to draw it just above so we can see it just above, right there. Okay, so now what I want to do is reflect this graph about the line, pardon me, y is equal to x. So that's the main diagonal. So we're going to look at the main diagonal here. And I can use the purple guy and reflect. So instead of going to the left 1 and up 1/2, I go to the right 1/2 and down 1. Instead of 0, 1, it's 1, 0. Instead of 1, 2, it's 2, 1. Instead of 2, 4, it's 4, 2. So we get this lovely logarithmic function, which is just a reflection of 2 to the x. So log base 2 of x about the line y equals x. So notice that my vertical asymptotes and my asymptotes change positions. Instead of a horizontal, I now have a vertical because I've swapped every x and y. Okay, so there we are. So that's one way to plot a logarithmic function, which might be easier Move this down just a bit. What I think I'm going to do also is write this 2 to the x in solid purple, 2 to the x. Okay, hopefully that makes sense. Okay, so moving on, let's recall. E is defined to be, so 3 lines means is defined to be, the limit as x approaches infinity of the quantity 1 plus 1 over x raised to the x. And that's around 2.7-ish. But we don't round in this class. Pi is pi, e is e, period. So definition. So number 1, the common logarithm. Pardon me. Common logarithm. That's what we're defining first. The common logarithm denoted log of x is given by log of x is defined to be log base 10 of x. Okay, let me write that base 10 a bit better. 10. Okay. So the second definition will be the natural logarithm. So the natural logarithm denoted ln of x is given by, so that's an ln of x, so is given by ln of x is defined to be log base e of x. Okay. So for example, so let's solve the following. The following logarithmic equations. Arithmetic equations. Okay, so number 1, let's say we have log, oh my goodness, holy free holy, really? Yeah. Log of 1,000 is equal to x. Okay, so log of 1,000 is really, it's equivalent to log base 10 of 1,000 is equal to x. Right? Because by definition, log without an indicated base is the common log, hence the base is 10. So we can translate this now from logarithmic to exponential form. So this now becomes 10 to the x is equal to 1,000. And actually this implication goes both ways. Okay, so 10 to the x. How many zeros is on this? There's 3 zeros here. So I know I can write this as 10 to the third. Because it's always 10 times, or 10 raised to the power is how many zeros are on the 1. Okay, so now I can equate the two exponents. Let me do this in yellow. So what this means is that the exponent x must be the same thing as the exponent 3. And there we are. We've solved for x. So we can say therefore, log of 1,000, remember it's common log, is 3. Okay, so number 2. Let's say we have log base 5 of x is equal to 4. Okay, so log base 5 of x is equal to 4. So this is equivalent to saying base raised to the answer is equal to the argument. So I can write this as base 5 raised to the exponent 4 is equal to x. Okay, what's 5 to the 4th? Well, that's 5 squared times 5 squared, which is x. So I claim that that's 25 times 25. So 25 times 25, or 25 squared, which is 625. Okay, so here we are, 625. Okay, so I guess we could be thorough, therefore. Oh, it's a terrible therefore. So log base 5 of 625 is equal to 4. That is, the power to which I raise 5 has to be the 4th power in order to get 625. So number 3, let's say we have ln of x is equal to 7. Okay, so ln of x is equal to 7. Well, that's equivalent to saying log base e of x is equal to 7, because that's what natural log, or ln, means. So now I can translate from logarithmic to exponential form. So this is going to be equivalent to e to the 7th is equal to x. And we're done, because that's what we're solving for, is x. So therefore, notice I didn't put that in my calculator. I didn't get a decimal approximation. I left it as the actual value. So natural log of e to the 7th is equal to 7. Okay, let's do another one, number 4. Do I keep on moving? No, I think I'm okay. So number 4. Let's say I have, pardon me, log of 0.00001 is equal to x. Okay, so log 0.00001, which is equivalent to log base 10 of 0.0000. See, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1. That's equal to x. So now I can change from logarithmic to exponential form. So this gives me 10. What color should I use? 10 to the x is equal to 10 to the, well, this is decimal, so it'll be negative. How many zeros precede the 1? 5. 1, 2, 3, 4, 5. And we always count the 0 preceding the decimal. So what that means is that, oops, do that in solid yellow lines. So this means that x is equal to negative 5. Okay, so therefore, I claim that log 0.00001 is equal to negative 5. Okay, let's do another one, number 5. So let's say we have log base x of 1/81st is equal to negative 2. Yeah, what the heck, let's make it positive 2. Okay, so rewriting this, we have log base x of 1/81 is equal to positive 2. So I want to translate this into exponential form. Base raised to the answer is equal to the argument. Okay, so this is equivalent to saying x squared is 1 over 81. Okay, so I can take plus or minus the square root. And here's where I have to ask you a question. So if I take the square root plus or minus, let me copy and paste this. Why am I only really allowed to take one square root? So I'm going to take the square root of both sides. But one of those square roots I can't have. Well, let's go back to the definition of a logarithmic function. Where is the definition of a logarithmic function? Here. The base a has to be greater than 0. So if the base a is greater than 0, and I'm solving for the base in this question, do you think I'm allowed to have a negative? No, I'm not. So I can only have the positive, right? Only have the positive. So we get that x is the positive square root. So the square root of 1 is 1, and the square root of 81 is 9. So I claim that the base, so therefore, we have log base 1/9 of 1 over 81 is equal to 2. Okay, so let's do another one, last but not least, for this little example. So let's say we have ln of x is equal to 0. Okay, so we have ln of x is equal to 0. Well, that's equivalent to saying log base e of x is equal to 0, because ln is the natural logarithm. So now I can translate from logarithmic to exponential form. So this gives us e to the 0 is equal to x. Well, all non-zero guys raised to the 0th power is 1. So 1 is equal to x. That was actually not so bad. So we get that natural log of 1 is equal to 0. And actually I should have put it there for. Forgot to put that. Okay, let's do one more set of maybe just 3 little examples, and then we'll be done with this sections. So example. So solve the following exponential equations. So solve the following exponential equations. Oh boy. Okay, that's just equations. Okay, so number 1. Let's say we have 3 raised to the x minus 2 is equal to 81. So we have 3 raised to the x minus 2 is equal to 81. So the goal is to get the same base on either side. Well, at the very least, I know that 81 is 9 squared, right? 9 squared. But I know that 9 is 3 squared. So I can write this as 3 squared quantity squared. And when we raise a power to a power, we multiply. So 3 raised to the x minus 2 is equal to 3 raised to the 4, because 2 times 2 is 4. Okay, so this implies, this implies that x minus 2 must be the same as 4, which means that x is going to be 6. So therefore, once I add 2 to both sides, so therefore, I have that 3 raised to the 6 minus 2 is 81. Okay, that was the x I was looking for. Okay, so number 2. Let's say we have e to the x squared is e to the x plus 6. Okay, so we have e to the x squared is equal to e to the x plus 6. Well, right away, since the bases are the same, I can just say x squared is equal to x plus 6. Subtracting x plus 6, I get x squared minus x minus 6 is 0. And now I can factor. So what two integers multiply to negative 6 and add to negative 1? How about negative 3 and positive 2? So in the first case, x is 3. And in the second case, x is negative 2. So the solution will be x equals to either negative 2 or positive 3. I didn't like this curly bracket. Let me make that a bit better. Okay, and last but not least, since third time's a charm, let's say we have 1 million is 10 raised to the x squared minus 10. Okay, so we have 1 followed by 1, 2, 3, 4, 5, 6 zeros is 10 raised to the x squared minus 10. So if I have a 1 followed by 6 zeros, that means that's 10 to the 6th is equal to 10 raised to the x squared minus 10. Okay, so this implies I can equate the exponents now. So 6 is x squared minus 10. So subtracting 6, get 0 is x squared minus 16. Well, that looks like the difference of squares if I draw. So I can factor this as x plus 4 times x minus 4. Meaning my roots are either negative 4 or positive 4. So the solution will be plus or minus 4. Both of them work. Okay, hopefully that makes sense, and I will see you in the next section.